This video is going to look at kinematics in 2 dimensions, or the study of motion in 2 dimensions without any consideration for the forces that are causing them, and a little bit of introduction to projectile motion, which was the main example we're going to look at when we look at 2D motion. Just as a reminder, our kinematics in 1 dimension, this is again the study of motion without any concern for forces. We looked at a few examples that I'm listing here: dot diagrams, carts on a straight incline. We looked at our graphs we can produce, and of course free fall is an excellent example of one-dimensional or motion in a straight line in which the gravitational acceleration little g is the constant value for that acceleration. In 2D motion, there are 2 main examples that we use for studying this in an introductory way. One is with uniform circular motion, in which the velocity or the speed, the magnitude of the velocity is constant, but the direction is constantly changing, and since velocity is a vector, it has a direction, and therefore if that direction is constantly changing, that has a constant acceleration. The other form or example is commonly used that we will use because we can study it in the lab is projectile motion, or launching something either horizontally or at an angle. And we will look at this in a few different ways this week. Main thing to keep in mind just for projectile motion is that in the x direction or horizontal direction, the velocity is constant and the acceleration is therefore 0. And in the y direction, it's just free fall. So we have a changing velocity where the acceleration is a constant g. We're going to give an example of kind of how this approach to studying 2D motion came about. The key to doing 2D motion is to analyze the motion in the x or horizontal direction and the y or the vertical direction separately. So I'm going to put stars by it, arrows by it, and a box. Analyze the motion in the x direction separate from the motion in the y direction. You're looking at what's happening in the x direction or horizontally as if the y direction stuff is not happening at all. And then you go and look at the y direction stuff, and you're looking at it as if the stuff happening in the x direction is not happening at all. They act independently, and they do not affect one another, and so when we analyze that motion, we analyze them separately or independently from one another. Here's a classic example, which we'll do a demo in class if we can. This is a matter of just dropping, so there are 2 identical billiard-sized balls here, one red, one yellow. The red one is being dropped just vertically, so it is in free fall. The other is being projected horizontally at a 0 angle. There's some time-lapse photography taking place in which the camera shutter is opening and closing at equal intervals of time, so it's producing kind of like a strobe light effect, so you can see the position of each ball at equal intervals or lengths of time having elapsed. I'm going to draw in some vector arrows here. All the vector arrows on this diagram are just going to indicate displacement or change in position. Blue is indicating my change in the y position. I'm going to try to keep everything in blue, the y direction, everything in x, or in red, the x direction, and my green will represent resultant or final values. We can see when I just copy and paste over those blue arrows from the free fall, the red object that's falling, those blue arrows match up almost exactly, they should be exact, but almost exactly with the displacement vertically of the yellow ball. You can see that the red ball is just in free fall, falling vertically. The projected horizontal one, an example of 2D motion or 2-dimensional motion, is also falling the same vertical displacement or the same vertical height for every interval of time as if the x motion or the motion in the x direction is not happening at all. There's one relation here that is historically important, and we can thank Galileo for it, and that's this relationship, as we can see from our kinematic equation, that the delta y, or the vertical displacement, or the fall height, the fall distance, is directly proportional to the time squared of the falling object, or how long it's been falling. That little alpha symbol there is also used to show varies with, or is proportional, no, not proportional, varies with is what I want to say. So that delta y, or fall height, or fall distance, varies directly with the time squared. So if I write out, say, the time intervals, or the units of time, which would probably be seconds, but it's fractions of a second most likely in this picture, as 1, 2, 3, 4, 5, etc. in gray, I can also write out the total fall distances at each point, which are squared in relation to that time. So I have 1, 4, 9, 16, etc. I can then look at the differences in between each of those blue values I wrote, and I get this relationship in orange of 3, 5, 7, 9, etc. I keep finding those differences. This orange distances I've listed, these are sometimes referred to as the odd number rule of falling objects, and it was something that was an astonishing discovery at the time, and it showed us quite a bit about free fall and the relationship that we now see in our kinematic equation, that fall time is directly related to the square of the time. Another fact that was discovered about and allows us to now analyze two-dimensional motion is that these two components of motion in the vertical and horizontal directions, or here in blue and red vectors, can be treated separately and occur as if one is not affecting the other, or look at it as if one isn't even happening. So as we mentioned, the blue arrows are representing that fall time, or that fall distance, I'm sorry, just as the one in free fall is, just like the red ball. And in the x direction, with the exception of that curiously longer first red vector arrow at the top that I put a question mark by, all the other red vector arrows in the horizontal direction are exactly the same. They're just copy-pasted over. So the motion in the x direction is happening at a constant velocity with zero acceleration. That's why the same displacements are there in red for each increment of time the yellow ball falls. And it's not affecting at all the vertical displacement that the yellow ball is experiencing. It's identical to what would happen if you just let it go and let it fall in free fall. I've written in now also in green the resultant vectors. These are all still displacements or changes in position. So when I add up one of the blue arrows and red arrows together, I get the resultant, which is the diagonal of the parallelogram that those red and blue vector arrows form. And if I add all of those up, and if I were able to increase the number of frames per second being taken by the camera and draw in even more vectors, I would get a quadratic function that is the parabola. And indeed, we have one kinematic equation that we can use for projectile motion that does describe that parabola. Again, written down here, I have that the resultant vectors in green are the sum of those two components added together, the magnitude of which we can find using the Pythagorean theorem. There's the diagonal that it forms in large green from the initial and very final positions of the ball. So that's how I can find the magnitude or the amount or the length of that hypotenuse that represents the final displacement. I also need to be able to find the direction. In this case, I can use my arctangent if I know the opposite and adjacent sides of the triangle I just drew, where the angle is there, theta, written in white. And if I'm going to find that, I need to use my arctangent function or some other arc function in order to determine that angle value. I need to think physically and be careful to write it out correctly, that this would probably be, if I were to describe it by convention, some negative angle in degrees that's measured negative or below the positive x-axis. I also have the values that I can find for the x and y components of my large green displacement vector. I've also written there down at the bottom that the delta x, or displacement in the x direction, can be found by multiplying the magnitude of my hypotenuse, the resultant vector, times the cosine of the angle. That provides me with the value of the adjacent side. And likewise, for the y displacement, I can multiply the magnitude of the resultant vector times the sine of that angle theta to get me the opposite side. I'm going to do an example problem here that is not actually projectile motion. It is an idealized motion, you say perhaps deep out in space, where there is no other gravitational force acting on this spacecraft. It's going to have some motion in both the x and y directions, and that's really what 2D motion is about. Isolating and being very careful about looking at each type of motion in the x direction and y direction, analyzing them as if the other dimension or other direction of motion isn't happening at all because they don't affect or change one another. We analyze them independently. And then being able to put them back together at the end to say what the final resultant values might be. So here's my example question. This can be found in your Cutnell and Johnson book in the 3rd chapter. There's some great check your understanding or CYU questions there that are good conceptual questions that are kind of AP style. And they also have some quantitative questions like this one, which is really good for practicing organizing our kinematic variables, which we will do now. In the x direction, a spacecraft has an initial velocity component of positive 22 meters per second and an acceleration of positive 24 meters per second squared. In the y direction, the quantities are 14 meters per second and 12 meters per second squared, respectively. Notice the units there indicate to me easily which value is which. 14 must be the velocity because it's meters per second, and 12 must be the acceleration because the units are meters per second squared. At a time of 7.0 seconds, determine A, the craft's total displacement and velocity in the x direction. So by which I mean tell me what is the x displacement, or the delta x, or displacement in the x direction of the craft. And also, what is its final x velocity at its final position, as you can see in the diagram. That vector is actually already drawn in. Part B is going to ask the same of the y direction, its displacement vertically or upwards in my diagram. And as well as the velocity, which is also already drawn in on the diagram. And part C is going to say, okay, now find the final velocity, resultant velocity of those two components added together. First thing I'm going to do is draw out a t-chart, which is just a little table to help me keep my kinematic variables organized from the x and y directions. I'm going to go back to my problem and circle those values in red for the x direction and blue in the y direction. Tell me identify what those are. I notice I have my initial velocities and my accelerations for each direction of motion. I'm writing out those 5 kinematic variables in my t-chart, being sure to keep my subscript straight to indicate which direction is which. And notice that my time at the very bottom there, that's simultaneous. The time in the x direction is going to be the same as the time in the y direction because the object is not splitting and occupying 2 different points in space at the same time. It is a macroscopic object, not a quantum one. So here we have me listing in our initial values that I know and making sure I put them with the corresponding kinematic variables in the x and y directions respectively. I look in part A, what am I looking for? The displacement in the x direction, that's my delta x. So I got an orange box indicating that's what I'm looking for. And I'm also looking for the final velocity in the x direction, v sub x. I'm writing in my seconds there. It looks like I may need to write something again. And then I have a vector. I've decided to annotate my diagram to help me further visualize what's going on and make sure I'm doing the right thing. So I have a purple vector I've drawn in to indicate where my x naught or initial x position is, and I used x sub f to indicate my final x position. So when I solve for delta x in my equations, what I'm really solving for is the amount or magnitude of that purple vector as well as its direction. So that's going to be a positive direction if my 0, 0 origin is over there where the lighter kind of watermark of the spacecraft is at what looks like the origin, and so long as I call the positive direction to the right, which my diagram already indicates. I've also drawn in there just the relative size of the velocities and how they're represented in the diagram, which comes from the book. Now I'm going to write through the kinematic equations that I'm using to solve for the variables that I want. I need to look through those 4 kinematic equations to decide which one's useful that I want to use. So I started with my first one there to find the final velocity in the x direction. I check my significant digits in a problem like this. I notice I have 2. I should in my t-diagram have the seconds or the time as 7.0 seconds. That's what it's given us in the problem. So I have my final velocity there of 190 meters per second. It's in the positive direction, and it has 2 significant digits. As far as finding my displacement goes, I have 2 possible equations I've decided to use, and I can use one to check my work from the other. So notice here I'm keeping track also of the units that as they cancel out. That helps me make sure that I'm not making any mathematical mistakes and making sure I've used or copied over my kinematic equation properly. You also see some writing like that 490 plus 98. That's me doing kind of a little bit of mental math and taking notes because I'm not using a calculator. Notice both equations give me a positive 742 meter displacement in the x direction. I've reminded myself this is what I was representing with my purple displacement vector, and that is indeed what I'm going to put over in my answer box there, but I've noticed I had to round to 2 significant digits because that's what I'm starting with in my data. One of the nice things is we're always pretty much able to use some other kinematic equation, or when it comes to other sections of physics, different types of laws and equations to double check our work. So when we are looking for quantitative answers, we have a lot of ways to check to make sure we are doing the right thing, and therefore have a lot of confidence when we put our final answer in a box. Part B is asking for the same stuff but in the y direction. I've drawn that in as a y displacement in pink up on my diagram with a y naught and y final there. That y naught really should be on the where the y-axis hits the spacecraft, but I'm just trying to make it clear that it matches up in the same kind of displacement with my my purple vector arrow. I've done the same thing and used the same equations in part B to determine the final velocity in the y direction, which I have a positive 98 meters per second. And I've used the same 2 displacement equations to determine my positive 392 displacement in the y direction. Notice that I've rounded my 392 meters to a 2 significant digit value of positive 390 meters. I should pause for a second to think about the physical reasonability of our answers and how consistent this is with what our picture presents and the problem is asking. Notice that in the x direction I had an initial velocity of 22 meters per second and a final velocity I determined was 190 meters per second. This indicates that the object was speeding up. And indeed, if that's the case, then the direction of my initial velocity and my acceleration should be the same direction. And they are both positive, so it makes sense that the object is speeding up and the final velocity is greater than the initial velocity. Likewise, in the y direction, I should notice that my acceleration is positive, my initial velocity in the y direction is positive, and therefore my final velocity in the y direction should also be positive and larger. It is indicated that the object has sped up. So this is physically consistent, not only with those graphs that we talked about and the directions of our velocity and acceleration, but also makes sense with what we see in the diagram of the picture that's presented in the problem. Notice that both my velocity vectors in the original picture are larger than those that are in the initial position. In part C, I'm looking for the final resultant velocity. This is a matter of determining what the final resultant vector is for the velocity of the spacecraft. It has motions in the x and y direction, but these are being combined to produce one final velocity. This can also be said for the x and y displacements as well. That would be the final arrow, the hypotenuse that connects the base or the beginning of my purple vector to the arrow or final arrow of my pink vector. That would show me my displacement since I was using the purple and pink vector arrows to represent displacement. Part C question, though, asks what's the final velocity, and those are represented by the two final velocities in the x and y directions in red up by the final darker picture of my spacecraft. I've drawn in the initial parallel lines, which I indicate with the single and double chevrons to show that they're parallel, and the parallelogram is one way of visualizing the addition of my vectors. I'll draw in the final resultant vector. There it is in green. That value is the final resultant velocity, and it's the combination of the velocity in the x and y directions. Recall that finding the magnitude of this vector is done using the Pythagorean theorem most often. It's usually the quickest way to get it, and we have the values that we need. So I'm going to write out that Pythagorean equation, or Pythagorean theorem. I did a little estimate of the square root of 5 times 10 to the 4, and when I put in the calculator, it's about 223.6 meters per second. Since the final resultant velocity is a vector, it needs both a magnitude and a direction. With my x and y components, I usually can just say positive or negative in the x or y direction when I'm giving the direction of those vectors. For my final resultant velocity, though, in this case, you can see it's not actually just in the positive or negative, but it's somewhere in between, and I need to give this using some degree or radian measure for the angle. I'm using my arctangent function here because I have the opposite side of that right angle triangle I drew, and I have the adjacent side. That opposite side is the final y velocity, and the adjacent side is the final x velocity. Notice where I've decided to pick my angle. It is possible to use the other angle or some other angle in that triangle to indicate the direction of the velocity, but it's usually convention and good practice to measure the angle from the positive x direction. Notice my final angle and magnitudes that I've found. I've rounded to 2 significant digits, and also think about here the physical reasonability of our final answers. I had a Vx, or final velocity in the x direction, that's 190 meters per second, and for the y direction, about 100. So my hypotenuse of that triangle should be larger than both of those values, and it is. It's about 220 meters per second. So my hypotenuse's magnitude makes sense. Also think about the angle. I have an opposite side that is shorter than my adjacent side, which indicates that my angle should be less than 45 degrees, and it is. It's about 27 degrees. I've boxed my final answer and made sure my significant digits are appropriately reflected in my final answer. That's it for this problem. The keys here, remember, for two-dimensional kinematics are 1. Analyze the x and y motion of the object separately. The x direction stuff happens as if the y direction stuff isn't happening at all, and vice versa for the y direction. What happens in the y direction happens as if what's happening in the x direction isn't happening at all. We can separate them out and keep track of them using a T diagram I've done here in the bottom left. I'll list out my kinematic variables, write in what I know, box or put a question mark by what I'm looking for, and as I find them, fill them in. That's a matter of using the correct kinematic equations, which is up to me which ones to use depending on what I think is most useful or relevant. I just need to keep track of what values I'm putting in where, and be extra careful I'm not throwing in some acceleration in the y direction for my acceleration in the x direction. This will be a big issue for projectile motion, where whatever is happening in the y direction is just free fall, and you want to make sure you don't substitute 9.80 meters per second squared in for some x direction acceleration. When we do get to projectile motion, which will be in the next video, we'll look at horizontal projectiles. Horizontal projectiles, kind of like that yellow billiard ball, where the initial launch angle is 0, and we'll also look at projectiles that are launched at some angle. That's it for this video. Be sure to come with questions, and we'll investigate projectiles and two-dimensional motion throughout the rest of the week.